Hello everybody, welcome back to another discussion dynamics. Today we'll start a new topic, which is momentum of particles. As you can see on our timeline, we closed three chapters, which are kinematics, kinetics, and work energy methods for particles. However, even though we closed them, I think that they can keep coming back in the future. Yeah, so you can kind of just maybe you should not forget everything you learned there. Okay, we'll see. Anyway, as I already said, today we'll start a new chapter, and today we'll focus on linear momentum of particles. And today I prepared just brief lecture overview and two examples. Sounds like a plan for today? Okay, so let's start. So here is my brief lecture overview. As usually, when we start new topics, we consider our particle following the trajectory, yes, and then I will just derive some equations. We're gonna do exactly the same thing today. So please recall this scenario that we have our particle P, and that particle P follows this trajectory. And that trajectory can be a straight line, it can be a curve, it can be an arbitrary trajectory, okay? Our particle has mass m, and additionally there is a net force F acting on our particle while it is moving along the trajectory. In work energy method, so now let's take a step back to what we were already talking about. So in work energy method, we started with F equals to ma, and we projected on the path, and we took an integral over that path, right? But if I can restate what I just said in a little bit simpler language, we cared only about how much distance our particle is covering. Yes, we didn't care about time the motion lasts, right? We only cared about the displacement of the particle, right? That's why we used this definition for acceleration, v dv ds, and we ended up with such form. Such form of work energy method. When it comes to momentum methods, the situation is totally different. We don't care about how much distance the particle covers. We only care about how much time the motion lasts. Okay, so that's why we are going to take the integral over time. Okay, so I will basically take our F equals to ma, and I will just multiply it by dt, and I will take an integral from time instant 1 to time instant 2, from time instant initial to time instant final. Okay, and now I would like to go for the other definition of acceleration, because also we know that our acceleration, vector-wise, can be expressed in such form, dv vector dt, and that means that our dv is equal to a dt. And I will just plug this in here, and you guys can see, hopefully, that this expression is dv. So I can actually write F. Okay, I can maybe leave it here. F dt, integral from t1 to t2, and this is equal to m dv, integral from t1 to t2. The integral on the left-hand side is called impulse. And we can find its value if we know the expression for f. So if f is constant, integration is easy, right? If f is given to us as a function of time, you must integrate, and you must figure out how large is the impulse acting on our system. Yeah, and integration on the right, the integral on the right is just will tell us what is the difference in momentum of our particle. Because if we solve it, we will actually end up with momentum at time instant final minus momentum at time instant initial. So if we simplify that expression, we can actually write down that mv1 vector plus impulse is equal to mv2. In other words, momentum initial of our particle plus impulse is equal to momentum final. Any questions? Yeah. Have I forgotten about anything? Yeah. Anyway, I think that the information I shared with you should be enough to solve the two examples we are about to solve today. Okay. So what, can I switch the board and solve example number 1? Okay, let's do it. Okay, so as usually, please read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have two bodies, right? We have car A and car B. In other words, we have two particles, right? Particle A and particle B. They both have masses, different masses, and I believe that they will collide, right? One of them will impact the other one. But before the impact, we know what's going on there. Yeah, we know that velocity before the impact of particle A points this way, and the velocity vector of particle B is here. Particle B goes down and goes south. After the impact, the two particles will be basically glued together, and their velocity afterwards is presented here. And the thing is that that collision happened on the road where the speed limit was 30 miles per hour, right? And each of the drivers tells us that they were obeying the rules, yes, that they were actually driving within the speed limit. And it looks like apparently one of them is lying, yes? And our job right now is to see which of them is lying. Yeah? And once we know that, once we figure that out, the authors of that problem ask us to figure out what was the speed of the car that was not obeying the regulation. Okay, before writing down that problem, before starting the solution of that problem, let me write down what we know. So I think that MAG is 3,600 pounds. MBG is 2,800 pounds. But actually, in this solution, I care about the ratio, you know. So MA divided by MB is 36 divided by 28. And also we know geometry, so we know that our beta is 30 degrees, gamma is 10 degrees, and they ask us to figure out whether velocity A is larger than velocity B, or velocity B is larger than velocity A. And once we figure that out, they ask us to find the speed of the fastest car. Find speed of faster car. Okay. I hope that the problem statement is clear. Am I right, or do you have any questions? Okay, so this is how I solve these problems. I just start with momentum diagram. Momentum diagram, where I show what is the momentum at the beginning and what is the momentum at the end. Okay, so I'm going to write here before, and I'm also going to show what happens after. So I believe that before we have such a situation. We have this car going south, right? So in here we will have MB, VB, and I think that the other car, that was the trajectory, right? So I believe that the other car was going this way. MA, VA. So this is the momentum of each bodies before they impact each other. Afterwards, we have such situation. We have these two bodies together, right? And they travel along this line. So this will be MA plus MB V final, right? Let me also introduce these angles here. I believe that this was 30, and I believe that this was 10. Okay, guys, any questions? So now this is the most important part of that problem, because I claim that the momentum of the entire system is preserved. Yes, I just would like you to pay attention to what I said. The momentum of the entire system is preserved. So of this momentum of each body separately is not preserved. These bodies change momentum. However, if we consider the system as a whole, the momentum is preserved. And why can I postulate that? I just want to use 3 arguments to postulate that. First of all, question to you. Is there any external force acting on the system? At least in this plane? No, exactly. Yeah, these are just 2 bodies that collide each other, yes? Nobody's pushing them, yes? They're just colliding each other, yes? Is there a friction in the system? No, not that we know of, yes? There's no friction, yes? And second reason, third question to you, are these bodies constrained in any sense? Of course, in this plane. Is there are these bodies, is there like a rope attached to any of these bodies? No. Yeah, exactly. These are 2 free particles that just hit each other, yes? There are 2 free particles, yes? They just hit, yeah? This is unconstrained impact. So that's why we can postulate that momentum is preserved, and that's why we can actually put equality sign between these 2 diagrams. So situation before equals to situation after. So we can write in here that momentum of the system is preserved. I'm going to underline system, okay? And why? because there is no external force. For the second reason, there is no friction. And for the third reason, there is no, maybe there are no, actually, yes, there are no external force, friction, and constraints in the system. Okay, so for these three reasons, our momentum is preserved. So I can actually write such expression. MA VA vector plus MB VB vector is equal to MA plus MB vector final, velocity final vector. Okay, so sum of these blue and black vectors is equal to this red vector. But that vector equation does not tell us anything. Yes, let's maybe look at this equation component-wise. Okay, let's see what happens in the x direction and in the y direction. Okay, so let me write in here. Let me project this equation on the x direction, and let's say that this direction is positive. Why not? And why? With this direction as positive. So what do we have in here? I have to project that blue vector, right? Okay, let's do it quickly. I need this component and this component. Pick, and 30 is here. So I believe that this is cosine, and this is sine. And also let's project this red vector, okay, on these two components. Pick. So this one will be MA plus MB, V final cosine 10 degrees. And this one has no other choice. This one has to be sine 10 degrees. MA plus MB, V final, sine 10 degrees. Okay, I think that now I am ready to write my momentum equations. So actually I call these guys momentum equations. So what do we have in the x direction? In here we just have MA VA cosine 30 degrees, and this is equal to MA plus MB velocity final cosine 10 degrees. Yeah, I think that nothing else happens in the x direction. How about y direction? In here we will have MA VA sine 30 degrees minus MB VB, and this is equal to MA plus MB velocity final sine 10 degrees. Okay, so we are done with our diagrams, and we are also done with our equations. I think it's a good time for questions. Are there any questions? Okay, so let's see how many unknowns do we have, yes? Because we definitely have two equations. Oops. We definitely have two equations. And now let's see. First of all, we don't know the initial velocities, right? Because the drivers didn't tell us what they were. And I also think that we do not know velocity final. So it looks like we have three unknowns. So it seems like it's not solvable, right? However, they don't ask to find the values of these parameters. Yes, they only ask us to figure out if VB is larger than VA. Yes, in the problem statement, they don't ask us to tell us what was exact velocity. Yes, to say it in more mathematical form, they actually ask us to find VB divided by VA. They ask us for the ratio, right? So I actually believe that this is solvable. If we are looking for the ratio, I think that these two equations are enough to figure that out, okay? And this is how I solved it yesterday. I believe that I took equation y and I divided by equation x, okay? So I just took this equation and I divided by this equation. Oops. Oh, that was unexpected. So I just did something like that. We can always do it, right? Also, I think that I would like to split the fraction on the left-hand side into two fractions, if you don't mind. So I just would like to take something is wrong. Why you are not listening to me? Uh-oh. Okay. Such things are allowed to happen, okay? I'm solving it real time. Wait a second. No. So I just want to take this equation. I want to copy it here. Yes, this is what I want to do. Okay, so I just want to split the fraction on the left-hand side into two. Okay, so basically, I just want to leave this fraction here. And I want to move this value here and divide it by this as well. Why? Okay. This is what I wanted to obtain. Okay. So now we can see that some of the things simplified, right? Because I think that we can get rid of mass m from this fraction and velocity a from this fraction. I think that also we can get rid of these two brackets and velocity final. Okay, and we ended up with tan of 30 degrees minus MBMA. So the ratio of masses I mentioned at the very beginning, VB, VA, 1 over cosine 30 degrees. And this is equal to tan of 10 degrees. So please observe that all of a sudden we have one equation and one unknown, where the unknown is this fraction. Okay, and we know everything else. So if you would like to figure out what is that ratio, just grab your calculators and obtain that VB divided by VA is approximately 0.4465. Yeah, we are almost there, because now I just have one question to you. Based on that ratio, based on this expression, which velocity is larger than the other? A, yeah. So that means that probably driver A was lying to, driver A exceeded the speed limit. Cool. So that means that this implies that VA is larger than VB. And this is answer A. Okay. But what was the part B? There was also part B, right? So let me scroll up the board. And I think that in here they ask us to just figure out what was the speed of the faster car, right? If the other car obeyed the rules, yes? So basically now part B. So if this is true, that means that our VA is approximately VB divided by 0.4465. And they told us to set VB to 30 miles per hour. And if we do that, we will obtain that VA was traveling with approximately 67.185 miles per hour. Okay, this is answer B. Okay, that's all when it comes to example number 1. Any questions? Okay, everything clear? Okay. So let's do example number 2 then. As usually, please read and understand the problem statement before we start our solution. At least in this direction, right? Because if there is no friction, if there will be no friction, there is a friction between them, but if there is no friction between this block and the ground, then the moment will increase in this direction, yes? That is one. Okay, so what do we have in here? We have again two bodies, right? We have our block and a bullet. What do we know about them? First of all, we know their weights, right? We know that the block weighs 10 pounds and the bullet weighs 0.03 pounds. I think that we also know the situation pre-impact, right? Because we know that the bullet travels along this trajectory with this velocity, which is 1300 feet per second. And I think that our block is motionless at the beginning, right? So I think that I specified that velocity as v with a subscript big M 0, and this is 0 at the beginning. Yeah, and after the impact, our block will have some velocity. So it will have velocity v big M final, and our bullet will travel along this trajectory this time with much smaller speed. Yeah, it's a significant reduction of speed of that bullet. Yes, before we had 1300, now we have only 50. What else do we know? Aha, we know that there is a friction between the block and the ground, right? And we know geometry. We know that this θ1 is 30 degrees, and we also know that the value of θ2. Is there anything else we know? I think there is one more thing we know. That the time of impact, the time of collision is 0.001 seconds, right? So basically, the time bullet covers this red trajectory. I'm not sure if you can see it. Yeah. So the time the bullet covers this trajectory inside the block, it takes 0.001 seconds. Yeah, I think that's all, right? Okay, and what they ask us for? They ask us to find average normal force acting on the system. So we will replace that ground with a normal force, right? And they ask us to find what is the average value of that normal force, okay? And in part 2, they ask us to find what is the velocity of big block right after the impact, okay? So we have two unknowns in here. Okay, I think it's clear, right? Yeah, let's dive straight into our solution. So this is how I solve this problem. I start with a momentum diagram again. Momentum diagram. And I will just draw what happens before. I will draw what happens after. And now, if you want to organize your notes, make sure to leave some space in between these two drawings, okay? Because something will happen in between these two time instants, okay? So before, we have such momentum of the system. We have basically our block that is motionless, right? Our velocity of mass m is 0. But our particle has some momentum, right? Our particle is here, and it has some m v0. And by the way, 30 degrees is here. This is 30 degrees. Okay, momentum after is following. We have our block here, and that block has some momentum, right? It has big M, velocity m final. And our particle follows this trajectory this time. Our particle is here. And it has such momentum. It will have little m, v final. And I believe that this angle is 60. Okay, so we know our momentums before and after. But before there is an impulse, right? In here we must show impulse acting on the system. And again, I consider the system as a whole, yes? I don't consider motion of each body separately. I consider the motion of the entire system, okay? So in here, I'm just going to show the block with the bullet inside. And I just would like to show all the forces acting on the system. So we will definitely have m plus mg. We will definitely have normal force coming from the ground. And I think also we will have a friction force. Yes, I think that there are no other forces acting on the system. On the system, right? Because there are some forces in the system. Yeah, for example, the reaction force between the particle and the block. Yes, they react to each other, yes? But we don't care about them because we consider the motion of the entire system. Okay, and since we are in momentum chapter, let's not forget about our integral. So we will just integrate these forces from time instant 0 to time instant final. So now I hope that you see what is the point of these diagrams. In here, I show momentum initial. In here, I show impulse acting on the system. And in here, I show momentum final. Do you see that? With such the diagram ready, I think that it's quite easy to write down our momentum equations. And again, let's write them in the x direction and in the y direction. So what do we have in the x direction? We should do some projections here, right? So let's do it quickly. So in here we have mv0 cosine 30 degrees, mv0 sine 30 degrees, and in here we will have mv final cosine 60 degrees, and in here we have mv final sine 60 degrees. Okay, so at the beginning we have mv0 cosine 30 degrees plus integral of minus tf dt from 0 to dt. And this will result in mv final cosine 60 degrees plus the momentum of big block, right? Plus big M v big M final. In the y direction, we have mv0 sine 30 degrees with a minus in front, of course, yes? It's going to be negative because it points downwards, right? Plus integral of n minus m plus m g dt, and this will result in mv final sine 60 degrees. Wow. Okay, so these are the equations we will operate on. But before we start operating on them, any questions? So far, so good, right? I hope that you all can see that these equations correspond to the diagrams, yes? Okay, so what did they ask us for in part 1? Find the average normal force. Find average n. Okay, I think that n appears only in the second equation. Do you see that? So I think that it's logical to take this equation and figure something out with it. Okay, so let me take that equation. And I want to rewrite it, actually. I want to rewrite it, but I will split that integral into two integrals, okay? So in here we will have minus m v0 sine 30 degrees plus first integral minus the other integral. Okay, and I believe that Professor Zinn covered that part yesterday in the lecture, because he covered that every single integral can be expressed in such form. N average times delta t. Yeah, because we must introduce somehow the average value of our n, yes, to our equation, yes? So basically, if you want to integrate any single function f, you can express that integral as f average delta t. Plus, I observed also that this integrand is constant. So I think that we can express our equation in such form: minus m v0 sine 30 degrees plus n average delta t minus m plus m g delta t, and it is equal to m v final sine 60 degrees. All right, we ended up with one equation and, surprisingly, one unknown, because the only thing we don't know in this equation is the value of n average. Every single variable in this equation, other than n average, can be replaced with a number. We know their values. Okay, so there's only one thing left. Plug in values, grab your calculators, and find that average is approximately 656 pounds. This is answer A. So this is average normal force acting on the system during that impact. Any questions? I don't see any, so let's do part B. And I think that in part B, they ask us to find this velocity, right? The velocity final of the block. So I think that it's logical, since we used this equation, the second equation in part A, let's use the other one in part B, okay? So I'm just going to copy it, if you don't mind. And let's see if we can figure something out in here. So I think that, first of all, our friction is kinetic. So we can plug this value here, don't you think? So I hope you don't mind if I just erase that TF, and I will just plug mu kn in here. Mu kn in here. Second of all, mu k is a constant value. This is constant. So we can plug it outside. We can put it outside of this integral. Yes? So we can actually write mv0 cosine 30 degrees plus mu k 0 delta tn dt, and this is equal to mv final cosine 60 degrees plus m vm final. And by the way, I'm just going to use exactly the same argument as previously. This is an average we just found times delta t. So let's rewrite the same equation for the third time. Yes, I know that you don't like it. I also don't like it, but this is how it will be right now. So this will be. Oh, I forgot about minus. Yes. Oh, little typo. Sorry. This is not plus. This is minus. Minus here. Minus here. Mu k, an average delta t, mv final cosine 60 degrees plus m vm final. Okay, so again, we ended up with one equation and surprisingly one unknown. Yeah, in this equation, we know everything besides this value. So again, plug in values, grab your calculator, and obtain that VMF final is approximately 2.25 feet per second. Okay, any questions? So that's actually all I prepared for today, but I would like to go for 1 extra percent, okay, if you don't mind, because I think that we still have 2 more minutes. Yes. So I just would like you I just would like to come back to part number 1, okay? And I would like to actually show you the expression, the explicit expression for n average, okay? If you don't mind. So if you solve this equation for n average, you will end up with such formula. N average is m divided by delta t times velocity 0 sine 30 degrees plus velocity final sine 60 degrees plus m g. If you plug numbers here, you will end up with such values: 645.9 plus 10.03. Let's compare these two values. Let's see what is the my goal in here is to show you what is the contribution of gravity when we talk about impacts. It's very small, as you can see. Yes, by the way, it is already small, yes? And this is due to this parameter. Our delta t is 10 to the power of -3 seconds, yes? But this is what they told us. This is what they told us, yes? This is how long is that impact, yes? So imagine what would happen if that impact is even smaller, yes? I can imagine smaller impact, shorter impacts, yes? That was quite short, yes? So if that impact is even smaller, let's say 10 to -5, this will be approximately 65. It will be 650, yes? 65,000, yes? And the contribution of gravity will be even smaller in that case, yes? And now the punchline. That's why sometimes, many times, we forgot about, we don't even include gravity in the impacts. Yeah? When we talk about impacts, we don't talk about gravity. We just care about the reaction forces and so on. With that positive information, I would like to thank you for today and wish you a happy afternoon. Bye-bye.